Welcome. Today I want to start the lecture by taking a step back. In the last few lectures we have discussed solids and our quantum view of solids. And today I want to start with something very different. Let's think of a quantum system. It could be a single atom, or it could be a molecule, or it could be a solid, it could be anything. But for simplicity, let's think just of a two-state system. We have two energy levels. One is associated to 1 and number 2, and each one of these levels will have its own wave function, psi1 and psi2. When we go back to the Hilbert space formalism, so these two wave functions, apart from being functions as such, they are also, or they can be treated or seen as if they were vectors. And we have all the formalism to demonstrate that these two vectors must be orthogonal because they are the eigen functions or eigenvectors of the Hamiltonian, which is an observable, or is the operator that corresponds to the energy, which is an observable variable, and so on. And I don't want to make these too formal, but the thing is, we can see these two functions also as if they were vectors in this abstract space that we call the Hilbert space. And these two vectors that are associated to the wave functions psi1 and psi2 are orthogonal to each other. That's the important thing. And when we built the Schrödinger equation, one of the things that we did in the construction of this equation was assuming that the solutions were either monochromatic or monoenergetic, and this is the same in the end because there is the relationship the energy equals h bar omega. So the fact that each one of these two wave functions represent a single frequency or a single wavelength or color or a single energy is natural. So one of the things that it's very clear is that since function number 1, the wave function number 1 and the wave function number 2 are orthogonal, is that if I manage to do whatever is needed to prepare the quantum system in state number 2, in principle, since these two are orthogonal, the probability of, if I prepare the system and I don't perturb it, I just leave it completely insulated from the rest of the universe. I prepare the system in state number 2. So it's populated here, as I said. This means that this is the vector or the function that represents the state in which the system is in. And let's say I leave it there without any interactions, and I go and grab a cup of coffee and come back and observe where it is. I would say the probability of finding it in state number 2 is exactly 1. And the probability of finding it in state number 1 is exactly 0. And that is because there is no interaction with any other systems. So I leave it in vacuum, there's no electromagnetic radiation, there's nothing around it, there are no fields, there's no charge around that is producing or perturbing the Hamiltonian of this atom or this system. So if it's well insulated in the middle of the space with nothing around it, I would say the probability of finding the system in state number 1 after I grab my cup of coffee or go for lunch or even go to sleep for several hours or even take a holiday for several days is exactly 0. So we will always find it in state number 2 and never in state number 1 because I prepared it in state number 2 and state number 2 is orthogonal to state number 1. So the probability of finding of this state collapsing to this state is exactly 0. So the probability, which we can write as psi1, psi2, which is an integral of the product of the two wave functions, is exactly zero. And therefore, I postulate that, for example, the lamps that illuminate your house or whatever you are, or the lamps that I'm using here to illuminate this TV studio, should not produce any electromagnetic radiation. They should not produce light. And that's just because what we do in general in these systems is we excite electrons with an electrical current. It doesn't really matter too much, or by increasing the temperature or something. And essentially, once they reach a higher state, there is no reason formally for them to relax. And while it's clear that they will try and they prefer to be, let's say, in a lower energy state, the probability of this transition happening just spontaneously is exactly zero. So spontaneous emission of radiation and spontaneous relaxation, whether if there is a photon emission or any other mechanism, it doesn't matter. The relaxation of the system from one quantum state to another quantum state of the Hamiltonian is exactly zero, and that is true. What I'm saying is not false. What I'm doing wrong, and we've all seen light bulbs around us emitting light and so on, is that I'm not taking into account the electromagnetic field. And I'm thinking of a quantum atom or a quantum material system, this two-level system, as if it was immersed in a classical vacuum. And the classical vacuum is really empty. There's nothing in it. And electromagnetic radiation, in principle, can be emitted in any way. There's no restrictions on the electromagnetic field as long as it follows the Maxwell's equations. The electromagnetic field can be exactly zero or can have pretty much any amplitude value and so on, and that is wrong. That's the part that we haven't really discussed. So far we have discussed material systems, atoms, molecules, solids, from the quantum mechanical point of view, and we have built this Schrödinger equation and found the quantum states for the Hamiltonian of the hydrogen atom, or more or less at least discussed them. We have spoken about the square well, and we have spoken about other quantum systems such as the harmonic oscillator, the quantum harmonic oscillator, and even crystals, and we've seen with the Bloch's theorem and so on that the bands should form and so on. But we haven't really discussed the interaction between the material system and the electromagnetic field. And this is what I want to do today. So if you think about it, what I said here is absolutely pristine and very clear. If I prepare the system in state number 2, and state number 2 is orthogonal to state number 1, the probability of finding the system in state number 1 after a while, without any interactions, is exactly zero. However, the existence of spontaneous radiation or spontaneous emission of radiation proves that there's something wrong in this logic. And what's wrong is our vision of the electromagnetic field. And electromagnetic fields also have to be seen in the context of quantum mechanics. And that's a part we haven't done. So let's think of an electromagnetic radiation. Initially, let's think of a, let's say a cube. So it's a cube of metallic walls, right? And in this metallic cube, in this cube of metallic walls, the question is, what are the possible state of electromagnetic radiation. So if we think classically, in principle, only a collection of frequencies will be able to survive in this cube. And these are the mode that has half a wavelength between the two walls. We can have the mode with one full wavelength between the two walls. We can have also the one with 1.5 wavelengths between the two walls, and so on and so forth. But so not every single wavelength is allowed in the box. It's just a bunch of them. So it's an infinite collection, but it's the intermediate wavelengths between two of these. For example, the wavelength in between the green one and the yellow one is not allowed in the box. You will, I mean, even if you send a pulse of electromagnetic radiation and close this box and then observe the modes that survive there, even assuming that the walls are perfectly reflecting and there's no losses in the box, only these wavelengths will survive, and the rest will eventually interfere with each other and completely destroy each other, and only these ones will survive. Okay. That being said, I mean, this is what we call a cavity, an electromagnetic cavity. And of course, there are other modes that are allowed. For example, we could now look for the wavelength that goes between the walls in the back and the front wall. And if it's a cube, the wavelengths will be the same as the ones we've already put in the other direction. And of course, you also have the modes that go from the top to the bottom. Okay, so it's a big collection. You have many, and if the dimensions of the box is not a cube but more like a parallelepiped, so with different sizes in the 3 different directions, then the wavelengths allowed propagating in one direction and the other direction and the other direction will be different, but this doesn't really matter. Again, it's just a discrete number of wavelengths that are allowed, and the ones in between, with the wavelengths in between, cannot survive in this box. Okay, so just for simplicity, let me move to a one-dimensional box. Again, this can be done in 3 dimensions. It's just making things a bit more complicated. So if we have the walls of the box, we said, okay, you can have the mode which has half a wavelength, the mode that has 1 full wavelength, the mode that has 1.5 wavelengths, and so on, right? So we have all of these are allowed. And now the question is, how much energy can I put in each one of these modes? And again, if you solve the wave equation that is basically, you can derive from the Maxwell's equations, what you will find is you can pretty much put any amount of energy into these modes. You could take a charge and shake it and put as much mechanical energy as you want into this shaking, and this energy will translate into radiation. And you could, in principle, put again as much energy as you want. So let's focus just on this first mode here. Okay. So again, I'll draw the cavity again here. I'll just focus on the first mode now. And in principle, I could put 0 energy in this mode. So this means that although we know it's just half a wavelength between the two walls, I could put zero energy into this mode. And if I could put also a little bit, or I could put a lot, right? And I could put maybe whatever this little bit is, I could put half of that or 1/3 of that. And I can put pretty much any amount of energy that I want into these electromagnetic modes. And the same applies to all the others. So the same applies to this one and this one and this one and all the rest. So I could, in principle, put whatever electromagnetic field, electric field amplitude I want, and in principle that's allowed. The only restriction in this classical electromagnetic box is that the wavelength should be a multiple of the size of the box. Okay? Right. So, great. And now the question is, what happens when we think of these quantum mechanically? And again, the math behind these classical electromagnetic cavity is basically the same math, is a wave equation, and is the same math that refers to elastic systems. So, for example, masses tied up with springs to a fixed point, or masses that are tied up to each other with springs. So the electromagnetic waves and elastic systems share essentially the same math classically, and is to be expected that quantum mechanically the same will happen. So quantum mechanically, the electromagnetic field and elastic systems should in principle share more or less the same type of wave functions and states and so on. This is true. I'm not going to justify it formally, but I just want to convince you that this is the case. And this means that we should treat each one of these electromagnetic modes as if it was basically a harmonic oscillator, but a quantum harmonic oscillator. And in the case of a quantum harmonic oscillator, I'll just make a little note over here. In the case of a quantum harmonic oscillator, the potential is a parabola. So if we put here the potential energy as function of the position, what we find is that the quantum levels of this system are equally spaced. So the spacing between all of them is the same. This spacing here, the spacing here between these two levels is the same as the spacing between these two levels, and is the same as the spacing between these two levels, and is the same as these two levels, and so on and so forth. So this is of course an infinite ladder of equally spaced energies. However, the spacing between the zero energy point and this first point is 1/2 of the spacing between these two. Okay, so basically, in the case of the harmonic oscillator, and if you are interested, you can of course find many lectures about the quantum harmonic oscillator, or you can find it in books as well. The rule that the energy follows for quantum harmonic oscillators is E equals n plus 1/2 h bar omega. So basically, the amount of energy that the harmonic oscillator can acquire is restricted to only these energies. And the really interesting is this omega. This omega is the frequency at which the classical harmonic oscillator oscillates. So if you think of a classical harmonic oscillator, you have, let's say, a wall or a fixing point. What you have is a spring and eventually a mass m, a spring with constant k. If you solve this problem classically, what you get is that this system has a natural oscillation frequency, which is called the harmonic oscillator frequency, and that's omega. And that's given, this omega is given by the square root of k divided by m. where K is this constant of the spring, and M is the mass that is being moved. And this means that the harmonic oscillator can only acquire a collection of energies, but not any energy. Again, classically, this is counterintuitive. I mean, in principle, if I have this mass tied up to a fixed position with a spring, I could pull it to any position I want, and in principle, with that, if I move it from this position to, let's say, here, it will acquire this amount of energy. If I move it over here, it will acquire this amount of energy, and that position could fall in between two of these quantum energies, or the energies, the quantum levels. And this essentially means that in the quantum mechanical version, I cannot just pull I cannot just give it any amount of energy that I want, which classically I do. I just pull it, I find the correct position, pull the mass, and leave it there and let it go, and this harmonic oscillator will acquire whichever total energy I want to give it. However, quantum mechanically this is not possible. Only certain amounts of energy are allowed. The thing is that when you do the math for a macroscopic mass, let's say 1 kilogram, and a K that is also macroscopic for a macroscopic spring, what you find is that these levels are so close to each other in terms of everyday energies that we cannot distinguish, or we cannot see the separation of levels, and it looks like a continuum, but actually only a collection of energies are allowed. And what this tells us is that if we do the math, and again, I'm not going to do it for the electromagnetic case, but this system, and by system I'm thinking only not just of the cavity, but exactly just this particular electromagnetic mode in the cavity, is very similar to a harmonic oscillator. It has a natural frequency, so this wavelength or this frequency that corresponds to the radiation between these two walls with half wavelength is determined. So we have a natural oscillation frequency, just the same as we do with the harmonic oscillator. And what will happen is that this electromagnetic mode can only acquire a collection of electric field amplitudes, and therefore of energies. So the energy is basically the square of the electric field. So these energies will actually follow exactly the same rule, since the mass of the elastic medium, of the elastic systems, and the electromagnetic systems is essentially the same classically. That can give you the idea that this will be true, and it is true actually. So this mode with this particular frequency or this particular wavelength will only be able to acquire a collection of energy. So I cannot put, let's say, these energies here in between. So this energy or this energy, but perhaps I can only have this one that has the arrow there, or this one over here, or a collection, but not the values in between. So this is a bit strange. I mean, classically, we're not used to this, but quantum mechanically, this is what happens. And this means that I'll just make a new drawing. So this means that this particular mode of the electromagnetic cavity, and I will draw it over here, can only acquire either this amount of energy, or this amount of energy, or this amount of energy, or this amount of energy. Again, remember that the amplitude of the electric field and the energy contained in the cavity are related to each other, but not the values in between. So all these amplitudes here in between these two and these two and these two possible amplitudes are not allowed. Okay, so and the same happens for other modes. So each one of these modes will now be in itself. We will think of it as if it was a harmonic oscillator or a quantum system in itself. So it's now the electromagnetic modes, right, that can acquire either this amplitude or this amplitude or this amplitude, but not the ones in between. And the same happens for the next mode that has 1.5 wavelengths and 2 wavelengths and so on in the cavity. Again, so these amplitudes here in between are not allowed. Okay? And first of all, this has several implications. I'll draw again the collection of energies that each one of the modes can acquire. So this is the energy is equal to h bar omega, where omega in the case of the green mode here will be the frequency that corresponds to this wavelength, the green wavelength, so half a period in the cavity. Of course, this will be a different frequency for this mode, and will be a different frequency for the next mode and the next mode and the next mode. So each mode will have its own quanta of energy. So the spacing between the amount of energy that you can find in this mode and in this mode here are different. But for each one of the modes, you will be able to either find one, sorry, I wrote it wrong. This is the quantum, so this is the amount of energy of the quanta, but the actual energies that the system can acquire will be En equal h bar omega times n plus 1/2. Okay, so there are again the implication is that the spacing between all these modes, or the energetic spacing between all these states of each one of the modes is given by this quantum energy. But we also have the implication that 1/2 of the quantum energy is the minimum state. So this state that I will paint here in white, for example, here, this one here, is the minimum amount of energy that we can find in the system. We cannot completely erase the electromagnetic radiation. So the quantum vacuum, even in the absence of any energy given to it, already has certain amount of energy that is inherent to the free space. What we find is that this amount of energy, the amount of energy that we can give or subtract from the electromagnetic field, that's what we call a photon. And it's this quanta, this particle of energy that we can either add or subtract from the electromagnetic field, what we call a photon. So the photon is this thing, this abstract entity at the moment that we can give or subtract from the electromagnetic field. So this contradicts also a little bit what all these theories that Planck initially gave, that the quantum the exchange of energy between material systems and the electromagnetic field could only be done in quanta, but the electromagnetic field could have any energy and also the material system. And that's the way he justified his initial way of seeing, for example, the harmonic oscillator, and why he could find solutions to the ultraviolet catastrophe. And so on. I mean, Bohr did something very similar when he constructed his model of the atom. He didn't dare to talk about photons and so on, but it was Einstein actually the one that introduced this this idea that first of all, the electromagnetic waves were not just waves, they were also particles, and that these particles had fixed amounts of energy that were related to the frequency of the radiation. So now that we understand things a little bit better, and I'm not saying we fully understand them, but from the quantum mechanical point of view, photons are this. These are packets of energy that we can give or subtract from the electromagnetic wave, from the electromagnetic field. And at some point, we have subtracted all the photons from the space, or for example, from this cavity, we could find a way of removing all the photons. Even in the absence of photons, we will still have certain amount of energy that is inherent to the free space, and that's what we call the vacuum fluctuations. And this means that this wave, I mean, if you imagine it as an oscillating rope, for example, or a string or something, it's basically, we still have this little oscillation with a little bit of energy, which I put here in the white color, and that's true also for this first mode of for this first state of the second mode and the third mode and so on. This ground state of the free space, or in this case the ground state of the cavity, contains all these modes, contains a little bit of an oscillation in the electric field or in the electromagnetic field that cannot be lowered anymore. We cannot subtract more energy from the box, so all the electromagnetic energy has been subtracted, but still there is a little bit of a fluctuation. So there are still electromagnetic oscillations that we can find and measure in the space, even in the complete absence of photons. One interesting thing is that, I mean, so far we have spoken about a cavity, but what happens if we make the cavity bigger? So if we change this length, and let's say we start making it big, what will happen is these modes, the mode that is over here and this mode that is over here, will start stretching and stretching and stretching. So this means that longer and longer and longer wavelengths are allowed. And this will also bring all the wavelengths that are allowed closer to each other. So basically, when we take the limit and make the cavity infinitely big, all is the equivalent of saying that all the possible wavelengths are allowed. So in free space, not in the absence of cavity, basically, everything I've said is still true. However, all the wavelengths are allowed. So the idea that there is a minimum amount of energy for each frequency is still valid. So this, let's say, half photon that is an inherent property of the free space is still true. And that's true for this wavelength, but it's also true for this wavelength, and in principle for any other wavelength, because in an infinitely big cavity, all the wavelengths are allowed. So all that I've said is still true, but in free space this is allowed for any wavelength. So each wavelength, you can think of each wavelength as a quantum system in itself, in which we can put energy only, or we can excite this quantum state, this electromagnetic quantum state, or this electromagnetic mode, with only an integer number of multiples of this energy that we see here. So what I'm saying is that even in the absence of cavity, just in free space, one is that these quantum fluctuations still exist, and second, we can only exchange energy, we can only give energy to the electromagnetic field or remove energy from the electromagnetic field in these packages. And these packages so happen to have also particle character, and that's what we call a photon. So photons are exactly this. Okay, now going back to the interaction of the electromagnetic waves and the material system. So when we think of the electromagnetic field as something quantum mechanicals. Now we know about the presence of these vacuum fluctuations and so on. What we have, and let me draw it again, we have the quantum system we drew initially. So we have, we have level number 1, level number 2. We have the wave function for each one of them. And we think of, for example, this system being populated in the upper level. So we already said as well that the wave functions, we can see them as orthogonal vectors. So this is psi1, psi2, and everything I've said so far remains true. So these are orthogonal to each other. So in principle, we don't expect to have any spontaneous transition from state number 2 to state number 1. However, these vacuum fluctuations, if you think of the electromagnetic potential, so whatever the potential was for this system that we have here, let me just draw here for a second the Schrödinger equation. So we have minus h bar squared over 2m Laplacian plus the potential of R. These applied on the wave function equals the energy times the wave function. So whenever we apply whatever the potential we were using, I mean, this system can be an atom, let's say it's a hydrogen atom, for example. We will have to put here the potential that corresponds to the Colombian interaction between the nucleus and the electron, and we solve it and so on, and everything we have said again so far is true. However, to this potential we will have to add an extra term. So here we will have to add an extra term, which is this electric field that is the fluctuation of the vacuum. This little bit of oscillation, which is very, very mild, is just very, very low in amplitude, but still present in the vacuum. So even if the system, if this hydrogen atom, we put it far, far away so that it cannot interact with anything else, it will still feel this extra electric field that is fluctuating there. Again, this electric field is very small, so so the amplitude is not going to be very significant, and mostly the strongest interaction the electron will feel will be the attraction to the nucleus. However, there will be this very small perturbation, and what this will mean is that we prepared the system in this state here that we call psi2, okay? But let's say we wait for a little bit of time, and this electric field, this fluctuation of the vacuum appears. So this means that a little bit of an extra force will appear on the electron, and this will change the potential. It will change it just a little bit, not very much. And this means that the Hamiltonian now will be a little bit different, and therefore the solutions will be a little bit different. They will not be very different, they will be just a little bit different. So I will draw here, and I will try to make it very similar. So this is just a little bit different, and also the other solution here will be a little bit different. So when this vacuum fluctuation has imposed a little bit of electric field on the atom, and therefore perturbs a little bit the Hamiltonian, it will have perturbed the eigenstate of the quantum system. So this means that there will be this very small, although here it looks big, it's really a very small change. But there will be these very small changes in the wave functions. So the wave functions that solve this new Hamiltonian that has a little bit of electric field pointing in one direction or the other will be slightly different. So if these are the original vectors, the the perturbed wave functions will be this. Remember, this is fluctuating all the time, so the vacuum is imposing this electric field all the time. So this thing is going to be randomly moving around a little bit. So they will not change completely there. I mean, it's not going to be a big change, but the wave functions will, the eigenfunctions that solve the Hamiltonian from one moment to the next one, to the next one, to the next one, depending on this fluctuation, will be a little bit different. So the wave functions will be fluctuating a little bit. And this means that if we prepared the system in state psi2, but now the solutions to the Hamiltonian, because of this fluctuation, are not psi2 and psi1 anymore. They are psi2 prime and psi1 prime, okay, momentarily, okay, because of these fluctuations. So they changed a little bit. And if we wait a little bit more, then it will change again, and it will be fluctuating, as I said. But let's just take a picture for a second. So this fluctuation changes things a bit. Now we are looking at the moment in which the green wave functions are the solutions to the Hamiltonian. And this means that, yet, the system, we prepare the system in the state psi2, not psi2 prime. So the system will still be in the state psi2. However, the state psi2, if we are very strict, will have a little bit of a projection into the state psi1, okay? So the probability of a transition is no longer 0. So now if the system is in state psi2, but the eigenstates of the system are psi2 prime and psi1 prime, now the probability of finding it in psi2 prime is very high, of course, because the projection of psi2 on psi2 prime is very big, so it's this much. However, there is a tiny probability of finding the system in state psi1 prime, okay? And this means that now the transition is possible. It's still unlikely, but it's possible. However, this is fluctuating all the time. So with time, eventually, the transition will occur. And in principle, the system can change from the average state psi2 to the average state psi1. And that's just because all the time now we're having a little bit of a projection between the state where we put the quantum system and the actual ground state that the system has in each moment due to these fluctuations. So I hope I didn't make it too complicated, but the thing is, now this transition in principle is possible to the state psi1 prime, okay? So the transition from state psi2, that is where we left it, to the state psi1 prime is in principle possible, and it's just a matter of time before it happens. And this transition, in principle, and if all the rules that apply occur, can happen by the emission of a photon. So what we see is that the vacuum fluctuations allow the system to transit from one quantum state to another and emit electromagnetic radiation. So they produce somehow spontaneous, the electromagnetic field itself produces spontaneous emission of radiation. And this is basically what the view of a quantum system that is now immersed in a quantum vacuum. Okay, so just to summarize, we have discussed a little bit of why a quantum system in a classical vacuum should in principle have no spontaneous transitions. From there we moved on to try to understand the electromagnetic field, but now from a quantum mechanical point of view. And although we didn't do any math or any formal treatment of the electromagnetic field, I hope I more or less convinced you of what is the correct way of seeing the electromagnetic field from the quantum mechanical point of view. This electromagnetic field from the quantum mechanical point of view can now only acquire energies in quanta that we call photons. And these photons also have particle character and so on. So these things that we've already discussed in previous lectures. But the most important thing is that the electromagnetic field can only receive or give energy to material systems in this quanta, and that's the only allowed state of the electromagnetic field itself. And second of all, there is this vacuum energy or this ground state energy of the vacuum itself. So even in the absence of everything, of matter, of photons, of everything, there is a little bit of energy in the electromagnetic field, which produces fluctuations of the electric and magnetic field even in the absence of everything. And these fluctuations, we call them vacuum fluctuations, and these vacuum fluctuations are actually responsible for perturbing the material quantum systems enough to allow the existence of spontaneous emission. So that's all I wanted to say in terms of the electromagnetic field. I hope this is useful and gives you a little bit more understanding about the nature of the electromagnetic fields from the quantum mechanical point of view. And I also hope that with these we can now move on to trying to understand other aspects of materials and how they interact with the electromagnetic radiation. So thank you very much for listening, and I hope to see you in the next lecture.